Hi and welcome everybody to the 14th lecture of Digital Communication course. In today's lecture, we will be talking about offset quadrature phase shift keying or shifted pi over 2 QPSK. In the previous lecture, we talked about quadrature phase shift keying, and we said the key difference between quadrature phase shift keying and binary phase shift keying is the fact that we are using two basis function, two orthogonal sinusoids, sine and cosine. And due to this, what are the benefits that we gain when we use two basis function? We increase the spectral efficiency, we send more data rate within the same bandwidth, or we use half of the bandwidth for sending same data rate. And we said this is significantly very important in wireless communication system, and that's why we usually prefer to use a QPSK whenever we want to increase the spectral efficiency of our system. And we remember that we drew the constellation diagram of QPSK, and we said this is the figure you are seeing here, or the diagram, we call it the constellation diagram. And this is visualization of where you place your symbols in the I and the Q diagram. So this is not something you can see in real practical life, but you just use it to visualize the effect of your modulation on the amplitude and phase of your carrier. So basically, this is for understanding and visualization. So you can see this diagram, for example, in the spectrum analyzer. This is a device, you can buy it to analyze the signals on the air. So there is an option where you can have a window that shows you the constellation diagram of your received signal. So in the constellation diagram of QPSK, as you can see here, what do we have? We have symbols which are denoted by S, S1, S2, S3, S4, and each symbol is placed in a quadrant. For example, we call this Z1, zone 1, which contains the first symbol, S1, and this S1 actually in the fourth quadrant. Basically, to implement the QPSK modulation, you need to follow a mapping table to establish a rule. And this rule basically maps the bits into symbols. And these symbols are, in QPSK, represents the phases. All the symbols, they have the same amplitude, they have the same frequency. The only difference is the phase. Phase determines where each symbol is located, in which quadrant or in which zone. So for example, when you have 0, 0 and 0, 0 comes, you put your symbol in the third quadrant, S2. When 0, 1 comes, you put it in quadrant 2. This is 1, this is 2, this is 3, this is 4, quadrant 4. So 0, 1, quadrant 2, 1, 1, 0 in quadrant 4, 1, 1 in quadrant 1, this is 2, and this is 3. Now one might ask, can I change the quadrants? Yes, you can. You can say that 0, 0, I can put it in 1, 0, 1, I can put it in 4. It's up to you. You can do that. I just put this as a rule. But once you define it, you must stick with it. You must let the receiver know that you have used this, so that the receiver, when the receiver performs the demapping, he doesn't get confused or demap to something which is wrong. The transmitter and receiver should agree on the mapping table. This, we call it mapping table. And this defines the rule for your modulation scheme. Now, I just want you to note that the phase difference between S1 and S4 is pi over 2. S4, S3 is also pi over 2. S3, S2 is also pi over 2. S2, S1, the phase difference is pi over 2. However, if you move from S2 to S4, how much is the phase difference? 180 degree, which is pi. And if you move from S1 to S3, how much is the phase difference? It's also 180 degree, which is sudden change in the phase. And this causes also sudden fluctuation in the amplitude of your signal. Now, this kind of fluctuation, we don't like it in practical wireless communication system design because this sudden fluctuation causes sharp transition in the amplitude of your signal, not smooth transition. Now, this sharp transition, everybody knows that sharp edges in the rect, for example, they are impractical pulses, impractical shapes. In reality, you cannot generate them. So imagine you are doing these sharp transitions, sharp edges. You end up having something like this. This appears like discontinuous signal. And this discontinuous signal, when it passes through power amplifier or a filter, it causes peak to average power ratio. Also, it causes intermodulation products. Intermodulation products, they are kind of adjacent channel interference. So your signal spreads. When it spreads, it causes interference to adjacent symbols, and this is what we call it intersymbol interference. So we don't like this. We like to have smooth transition, not sudden, so that the amplitude or the signal stays continuous, not discontinuous. So basically, this is what motivates the study of offset QPSK. This is why we are studying offset QPSK, and this is the key difference between QPSK and offset QPSK. Offset QPSK tries to avoid these transitions. We don't want the symbol to have sudden fluctuation, sudden phase shift, large, like pi or minus pi. We want it to have only smooth amplitude transition, which corresponds to similar phases. For example, just pi over 2 or minus pi over 2. So to demonstrate this and make it clearer to you and to understand it in a much better way, let's take this. This is the data stream, yes? This is the data bits that I can give you in the exam and tell you modulate this data stream using QPSK. You show me the in phase. It depends on what I ask you. If I tell you draw the in phase, quadrature, and the final signal, you just for the in phase you take the odd bit values. Yes, odd bit values. And you map them to signals, to the sinusoids. You draw the waveform according to the incoming bits. And you take the even numbered sequence and you map it to phi 2 of t, which is the second phase. And then you sum the two signals. The summation of the two signals bring a new signal. We call this QPSK waveform. Now, as you can see here, do you see with me here, this point? This is not good actually in communication system, this transition. As you can see, if I tell you from math point of view, is this continuous? Discontinuous. Can you find the derivative at this point? You cannot. So this discontinuity produces interference, produces large amplitude fluctuation when it passes the power amplifier. It produces out-of-band emission. Not good to the system, so we want to avoid that. So you see, when I was telling you, you find a problem in something and try to find a solution. This is kind of a problem in QPSK. We saw it. It's not a problem in the bit error rate or spectral efficiency. It's a practical problem, and they proposed a new solution to address this problem. These are the things I'm asking you to do in your project. See a problem and propose a solution. When can you propose a solution, or when can you see a problem? When you are deeply understanding the thing. When you understand, really not memorizing, not just know how to solve things but not knowing the intuition behind them or the interpretation. So this is example on your project, for example, similar to it. Now, these are the facts that you need to know about QPSK. Whenever both bits are changed simultaneously, a phase of 180 degrees occurs. Yes? From where this information I extracted it? From here. 0, 0 to 1, 1, if I move, what's the phase difference? 180 degrees. If I am 1, 0 and move to 0, 1, 2 bits are changed simultaneously. What's the phase difference? 180. So basically, you don't need to memorize this. If I bring multiple choice, for example, and say when 2 bits are changed simultaneously, what's the phase difference? You have this in your mind. You don't need to memorize that, and you can answer it's pi or minus pi. At 180 phase shift, the amplitude of the transmitted signal changes very rapidly. From where did I get this information? From here. These facts are basically observations. Yes? From here, as you can see here, when I have 180 degree phase shift, the amplitude changes suddenly. There is discontinuity in the signal. So again, this is not for memorization, yes? And this sudden fluctuation, this sudden change in the amplitude causes amplitude fluctuation. This signal may be distorted when it's passed through a filter or nonlinear amplifier. Clear? This is the problem that we are trying to address. This is the QPSK signal. This is the filtered signal. This is the original QPSK, and this is the filtered after filtering. The filter tried to smooth things, usually. But now, to solve this problem, the amplitude fluctuation, which is this, yes, because it causes what? It causes amplitude fluctuation and distortion to the signal. To solve this amplitude, we propose the offset QPSK. So see, it's systematic. There is a problem, motivates us to find a solution. While we are finding a solution, we end up having a new modulation. And it becomes part of the literature, part of the science. Offset QPSK, what's offset QPSK? Offset QPSK says the data in quadrature component, yes, you have in phase and the quadrature. The data in the quadrature component, you delay it by t over 2 second, which is half of the symbol. If you do this, there will be no way that both bits can change at the same time. So when you do this, you avoid the sudden change. You don't have this change of pi or minus pi at all. You have change only by pi over 2 or pi. But how does this happen? Can we see together how does this happen? See, this is the first one here is what we have, QPSK. When we have sudden change, 0 changes to 1 and 1 changes to 0, we have pi, yes? We have phase change by pi, which causes amplitude fluctuation in the QPSK signal, and this is the problem we want to solve. Now, what do you do to solve this? You just you see offset QPSK, how easy it is. You just offset this this quadrature component, you delete by t over 2, which is half symbol. So this, instead of starting from here, yes, everybody with me, instead of starting from here, you start from the middle of the symbol and you continue. Now you have here change from 0 to 1. While you are having this change, here you don't have any change, it's 1. So the 2 bits are not changing simultaneously. This is what offset QPSK is really. So at the end of the day, you get a signal which is something like this. Somehow no big transition, you have like kind of smoother. This is offset QPSK. So at the end of the day, offset QPSK, instead of having a constellation diagram where the symbols can change their phases by over 2 or by, yes, you have a constellation diagram that can change its phase by only pi over 2 or minus pi over 2. This is the switching between the message point. This is for QPSK A, and this is for offset QPSK. Is it clear? Now you know the reason. What's the problem in offset on QPSK? You know how to solve this problem using offset QAM. Now you know what's offset QAM. Now what's we need to check the spectral efficiency and bit error rate of offset QAM. As you can see, are we changing the number of levels? So there is no change in the spectral efficiency. Are we changing are we putting more symbols close to each other so that the distance between them reduces and therefore more errors will occur if noise affects them? No, then obviously we'll have the same bit error rate. So bandwidth of the offset QPSK and the regular QPSK is the same. I explained why. Also, from the signal constellation, here we have 4 points with the same distance between all of them, and here we have 4 points with the same distance between all of them. Then the bit error rate or the symbol error rate, error probability, is actually this, which is the same for QPSK and offset QPSK. So if I bring a question in the final exam, true or false, QPSK and offset QPSK have different bit error rate. True or false? False. They have the same bit error rate. Yes? If I say why, you explain to me why. Because they have the same number of constellation points which have the same distance among each other. Now, is this the only solution for the problem of sudden amplitude changes and fluctuation in the amplitude of the signal? No, you have come up with other solution you can come up and produce. For example, another alternative solution that can do the same thing that offset QPSK does is pi over 4 shifted QPSK. What do you do in this? You use 2 constellations. This one and this one, and you switch between both of them. For example, when you have only change by pi over 2, you keep using the same constellation. When there is a possible change by pi, you shift to another constellation so that you avoid passing through the origin. You don't pass through the origin. What's the resulting constellation diagram? Since you are using 2, this one, yes, this constellation and this constellation. When you put them together, you have octa constellation, 8 points. The phase of the signal can be changed in this constellation by pi over 4 or 3 pi over 4. Plus or minus, of course. What's the phase difference between these 2 points? Anybody can tell me? Pi over 4. because the difference between this and this pi over 2. This is exactly in the middle, so it becomes pi over 4. Now, since the phase of the next will be varied in order of pi over 4 or 3 pi over 4, we can decide the differential pi over 4 shifted QPSK as given below in the table. This is the table. This is the data bits. You have the gray encoded data bits. You remember this is the mapping table, the rule that I use in my modulation. And the phase change in radians. If 0, 0 comes, what's the phase change? Pi over 4. If 0, 1 come, 3 pi over 4. If 1, 1 come, minus 3 pi over 4. If 1, 0 comes, then the phase change is minus pi over 4. This is kind of mapping table. Is this the only mapping table? No, you can't change it. But make sure you don't pass through the origin. You don't make the phase change by pi sudden. Okay? Then let's take an example. For example, this is an example that you can see, for example, in a question or this. Assume you have the following data sequence. And I tell you modulate this using pi over 4 shifted QPSK. You tell me, okay, the initial phase for each one of those 0, 0, 1, 0, 0, 0, 0 in which quadrant? Let's say in quadrant 1. What's the initial phase? Pi over 4. 1, 0 in quadrant 2. Pi over 2, pi over 4, and 0. These are the initial phases. Based on what? Based on the original position of the symbol in the constellation diagram. And you have now new incoming input data. New 0 random. So this is 0, 0 here. And this is 1, 0. You put it here. And another 1, 0. You put it here, and 0, 1, you put it here. Now, based on this mapping table, I said when 0, 0 comes, the phase change pi over 4. So you make the phase change pi over 4. So what's the transmitted phase, the final transmitted phase? Is this phase plus this current phase. Pi over 4 plus pi over 4, pi over 2. So what's the phase that you transmit your signal with? Pi over 2. This was pi over 2. And you changed its phase by minus pi over 4. What's the transmitted phase? Pi over 4. This was pi over 4. You changed it by minus pi over 4. The summation is 0. You transmit with 0. This was 0. 0, 1 comes, then you change the phase by 3 pi over 4, then the transmitted phase is this plus this, which is 3 pi over 4. Clear how to do the pi over 4 shifted QPSK? Then when you hear pi over 4 shifted QPSK? It's kind of offset QAM, another solution to avoid the problem of amplitude fluctuations in the QPSK signal, to reduce the peak to average power ratio and reduce the distortion. So this is offset QPSK. This is the comparison between QPSK and pi over 4 shifted. Pi over 4 shifted QPSK, sometimes we call it differential because it depends on the phase difference. So this is the signal of offset QPSK, and this is the signal of pi over 4 shifted QPSK for this data input. QPSK, offset QPSK, differential offset QPSK. Now, since we only measure the phase difference between adjacent symbols in pi over 4 shifted QPSK, there is no need for any phase information at the receiver side. We just care about the difference. Therefore, we don't have coherent receivers. We don't need coherent receivers. We have non-coherent. Non-coherent can be used. How to structure this? What's the block diagram of the transmitter? We have you take the input, the in-phase component I, the quadrature component Q, you find the phase of this signal, which can be taken by finding the tan inverse. Arctan is the tan inverse, everybody knows, but in MATLAB you use arctan, yes? Of this, the value here, and you find the angle, and then this is the phase of this angle. You delay it by t, and you subtract, and you take the difference. Phase difference. You compute only the phase difference, and then you transmit your signal with the phase difference. And at the receiver side, you just measure the phase difference between the current and the previous. The current and the previous. You don't need to know the exact phase of the signal. This is the phase. What's the difference? How much? For example, you received your signal with phase 3 pi over 4. You don't need to demodulate it. You don't know the mapping table. You just know, you wait. What's the phase of the second symbol? Pi over 4. 3 pi over 4 minus pi over 4 pi over 2. So this is the phase difference, and then I map this to the bits. This figure illustrates the possibility of phase angles wrapping around the positive real axis. So for example, this is the current symbol with phase theta k 60 degree, and this is the previous symbol k minus 1 with phase phi k minus 1 is equal to 350. What's the phase difference? This minus this, which is equal to 290. And this, in the mapping table, you see what's the value of bits corresponding to this phase. So basically, this is offset QPSK and pi over 4 shifted QPSK. And by now, you know what's the problem that offset and pi over 4 shifted QPSK solve, and the mapping table and how are they implemented at the transmitter and receiver, and the importance of both of them. With this, we conclude our lecture, and thank you for your attention, and meet you in next lecture.